So here we're asked to find the specific internal energy of water at a pressure of 7 bar and a temperature of 164.95 degrees C at a quality of 0.5. So since we're given that it's a quality, that there's some quality to the water, we know that it's a saturated liquid vapor mixture. So to determine that specific internal energy, what we're going to do is use the quality along with the specific internal energy for the saturated liquid state and the saturated vapor states to find the specific internal energy. So basically what it is the specific internal energy is going to be 1 minus the quality times the specific internal energy for the saturated liquid state plus the quality times the specific internal energy for the saturated vapor state. And remember that the quality is the mass fraction of the substance that's in the vapor state. So this is basically a weighted average. We're taking the property value for the saturated vapor, multiplying it by what fraction of the mixture is vapor by mass, and then taking the property for the saturated liquid, and then multiplying it by what fraction of mass is in the liquid state, and then that'll give us our final result. So in order to evaluate this, we need to know what this saturated liquid and saturated vapor properties are, the specific internal energy specifically. And before we do that, I'll just make a note here that the quality is 0.5. That's given in the problem statement. And to find what these saturated liquid and saturated vapor values are, we're going to go to the saturated liquid vapor mixture table for water, organized by pressure, since I'm given a nice even number here, or not an even number, but a nice number here for pressure, and then that should be the saturation temperature. So anyway, let's go to the table. So we're looking for the saturated liquid vapor mixture table organized based on pressure. Here it is. We said that the pressure was 7 bar, so we'll go down to the table here. Let me highlight 7 bar. You can see the temperature is exactly the temperature that we were given, 164.95 degrees Celsius. It's because we're in a saturated state. And then the saturated liquid specific internal energy is given right here. And the saturated vapor specific internal energy is given right there. So we need to remember those two numbers. So let's go back to our problem. And if the saturated liquid specific internal energy, just from that table, was 696.23 kilojoules per kilogram. And the saturated vapor specific internal energy was 2571.8 kilojoules per kilogram. So that just came from that table that we just looked at. So we can then plug those into our expression here to solve for the specific internal energy at our given quality. And that comes out to be 1,634.0 kilojoules per kilogram. And just to show you where we are on a TV plot and a PV plot, let's go ahead and plot the TV plot. So here's our vapor dome, and we're at a temperature of 164.95 degrees C, and that the corresponding saturation isobar for that one looks like this. And that pressure is 7 bar. And since we're dealing with a quality of about 0.5, that means we're somewhere in here. We didn't calculate the specific volume, but we could have if we wanted to, using this same formula, but using specific volume instead of specific internal energy. So that's what it looks like on a TV plot. Let's do it on a PV plot. Here's our vapor dome. Again, we know that we're under the vapor dome here because it's a saturated liquid vapor mixture. The pressure is 7 bar. It's an absolute pressure. Corresponding isotherm looks like that. Here's the temperature of 164.95 degrees C. And again, we're somewhere in here because our quality is about 0.5. This would be the same specific volume here as that you'd have over there. So that's where we are on these TV and PV plots. Okay, we'll end the example there.